Hello, and welcome to our Kraton SBC Inventor Series webinar focused on the engineered thermoplastics performance enhancement solutions for sustainable design. I'm Yulia Stream in Global Strategic Marketing, and I'll be stepping in for Brian to facilitate this session today. I'm pleased to introduce our key speaker, Luigi Balzano. Luigi is a staff scientist at Kraton, and he brings many years of extensive materials science experience, specializing in polymer physics and structure property relationships. Prior to joining Kraton, Luigi spent many years at Envalior in DSM, focused on polymer modification and processing properties. He works on development of innovation solutions for advanced materials at Kraton now. We'll start with a short introduction to Kraton, followed by a discussion of some of the key trends and target applications driving sustainable innovation. Then I'll turn to Luigi to spend the rest of time sharing our exciting innovation that can help boost performance of ETPs and enable lightweight design and thinner parts. We plan to use the last 15 minutes of our event for the Q&A. Please submit your questions using the questions tab in the bottom right of your screen. The webinar is being recorded, and you will get the recording momentarily. Kraton is the inventor of styrenic block polymers and a global leading producer of specialty chemicals. Headquartered in the Woodlands, Texas, we have 12 global manufacturing sites and 7 innovation centers to support our customers globally. This year marks the 5th consecutive year Kraton has received EcoVadis sustainability rating, which is a true testament to our focus on sustainability. In addition to active participation in the multiple industry associations focused on sustainability, 3 of our Kraton polymer plants are ISCC Plus certified, enabling us to bring certified renewable products to our customers. Kraton focuses on market-driven innovation to help our customers address key industry challenges across a broad range of applications. Our broad portfolio of solutions can be found in a wide range of end-use markets, whether it's automotive, medical, building and construction, or recycling, and many more. We believe sustainability, next slide, is among key innovation drivers across the different industry sectors. For ETP specifically, there are 3 macro trends that present opportunities for creating sustainability benefits across the value chain. Circular design. Today, product design demands a holistic approach, the one that incorporates the full life cycle assessment. And this means evaluating the types and sources of raw materials that are being used, minimizing the carbon footprint by reducing the use of fossil-based materials, and potentially incorporating recycled or renewable feedstock to enable circular economy and reuse at the end of life. Recyclability. Recyclability at the end of life has become a critical requirement across different applications, whether it's automotive, electronics, and many other applications that regulations and corporate commitments demand end-of-life recyclability. And finally, lightweighting. Beyond popular metal replacement with plastics, lightweighting can be achieved through designing thinner parts. With durability preserved, a down-gauged thinner part means reduced use of fossil-based material at the end of life, plus lower carbon footprint. In a moment, Luigi will share the technical data with you, but we are excited to discuss our recent innovation where our products can improve both impact strength and stiffness of ETPs. There's also an added benefit of improved flow, which is crucial to injection molding consistent parts. Applications are endless, but I wanted to highlight 3 of them. EV battery housings. These are traditionally made of steel and aluminum, but present opportunities for glass-filled PA6 or glass-filled polypropylene replacement if we can improve stiffness and toughness at the same time. The end result is a lighter part that can be mass-produced and injection molded. Electronics is another one where electronics are becoming more smaller and thin walling is critical Improving stiffness and toughness balance means reduced defects and scrap during manufacturing and increased reliability during the end use. Hydrogen-powered fuel tanks. Those have unfilled PA6 tank liners, and there is a potential for our additives to improve the hydrogen permeability. Another benefit across all applications is the addition of our material can help compatibilize regrind, which boosts the mechanical properties when reincorporated with virgin resin back into the product. Also, for further sustainability, these grades are available with up to 100% certified renewable content using mass balance approach. So before we present our solution, we wanted to poll your view on what do you see as the biggest benefit or need to improve ETP performance for your customers. Please take a poll question on the screen, and we appreciate your feedback. Okay, so it looks like people are still taking it. Okay, so it looks, okay, wonderful. All right, more people are taking it. So lower carbon footprint is leading the way for sure. And lightweighting and improved moldability are split, and then recyclability is at the end. Well, thank you for your feedback. Now I'll turn it over to Luigi to introduce our novel technology.
Thank you, Julia. ETP performance enhancement. Molecular blocks. By combining hard and soft segments, they achieve exceptional toughness and impact while retaining flexibility. A classical example of a Kraton block copolymer is SEBS. This is a tri-block copolymer structure where the end blocks made of polystyrene, the hard block, are linked by soft ethylene-butylene random copolymer. The physical properties of this material are controlled by a nanometer scale phase separation. In fact, as often in block copolymers, the hard and the soft block, polystyrene, and the ethylene-butylene random copolymer are physically incompatible. They tend to phase separate on the nanometer scale and form a morphology where the polystyrene hard domains are dispersed in a soft elastomeric matrix. Phase separation leads to a material that combines the properties of both blocks, and it is the basis for the thermoplastic elastomer behavior. When it comes to ETP modification, which is the topic of today, the block copolymer structure of interest is SEBS, where maleic anhydride is selectively grafted on the elastomeric segment. You can see it at the bottom of the screen. When regular SEBS is mixed with an engineering polymer, for instance, polyamide 6, the large difference modification of the mechanical properties. Of the polarity differences. In fact, maleic anhydride in the anhydride groups these copolymers act as a morphology compatibilizer, reducing the SEBS domain size by lowering the size till it becomes effective for modifying the mechanical properties of the polyamide. That leads to very, very interesting performance improvement. In the coming few slides, I will show some examples that demonstrate how Kraton malleated block copolymers enhance the properties of unfilled polyamide 6. Kraton has a versatile portfolio of SEBS functionalized with the maleic anhydride. There are 4 main products that differ mainly by styrene content and melt flow rate, as shown in the table on the left and in the plot as well. All these grades are suited for polyamide modification and adapt to varying application demands. The choice of the grade depends on the details of the target performance. The workhorse of this portfolio is what is called FG1901. This is a sort of a mid-spec grade in terms of styrene and flow characteristics. FG1901 has a long-standing track record of success in many applications in several areas, including the polyamide and polyamide 6 modification that will be further discussed in the coming slide. Building on this expertise, experience, and knowledge, we have now developed a new product specifically tailored for the ETP market modification. This experimental new product we preliminarily called as novel
Luigi, it looks like we are losing you. Perhaps we can turn off the camera and you can see if we can hear you. I apologize for this. So we have a bandwidth issue, looks like. Just 1 second. So maybe while Luigi is connecting, I can tell you that this experimental new product we are calling novel malleated SEBS or NMA SEBS. It is available for sampling, not yet available for commercial scale, but we are working on commercializing it very quickly. And the characteristics will be shared upon request at a later time. So what we would love to do to show you the performance of this novel modifier, and starting with the unfilled PA6. And so let's see if Luigi is back. Luigi, can you try to say something? Okay. So while Luigi is still disconnecting, so let me walk you through the slide, so he will rejoin us for a second. So please stick around. But what you see here is the data that includes the modulus strengths data. Yes, we can hear you. Please take it away. I just started introducing the slide, but it will be great if you do it.
Yes, thank you. I'm sorry for the technical hiccup. I'll try to come back, okay? So the properties here show a classical elastomer modification behavior of unfilled polyamides, where modulus and strength drop of a predictable. This results in a modulus, in particular, polymer rather than almost the same.
It looks like this sound. Okay. Maybe we turn off the camera, Luigi, and let's try to continue the discussion. Again, apologies for this technical difficulty.
Okay. So what I was saying is that the decrease of properties is almost the same for both modifiers, indicating that when it comes to tensile properties of unfilled polyamide 6, the changes in the molecular structure of the novel malleated SEBS have a little influence. This relates to the local deformation processes that are active in the material during tensile loading. On the other hand, when looking at the impact resistance performance, due to the different deformation mechanisms that are relevant at this loading condition, the situation is completely different. This slide shows impact resistance measured in terms of notched isotope, and it is clear that the new modifier exceeds FG1901, and it is not shown here, but it exceeds most other commercially available modifiers. Especially at room temperature, the impact enhancement is tremendous, about 10 times, but also with respect to the reference, but also at sub-zero temperatures, it's clearly visible. The remarkable improvement in impact resistance achieved with this novel malleated SEBS shows that when it comes to impact performance, choosing the right molecular design of the elastomer is absolutely critical to maximize the results. There is more to discover about functionalized and especially malleated SEBS. In this second part, we will explore how malleated SEBS can enhance the performance of glass-filled polyamide 6. The experimental study was designed to support the development of materials for applications such as EV battery enclosures via injection molding, where balancing tensile properties, impact resistance, and processability is crucial, and as you all know, a very difficult puzzle to solve. We chose as a reference formulation a common polyamide 6 material filled with 30% glass fiber suitable for injection molding application. This material was then modified with the go-to malleated elastomer Kraton FG1901, as well as with our novel malleated SEBS structure and an external malleated polymer as a benchmark. Just for your reference, if you worked with us previously, you know that we specialize in relatively soft materials, and our lab equipment is specifically selected to handle them. Therefore, to produce these hard and abrasive compounds, we prefer to cooperate with an accredited third-party lab in Germany who specializes in making glass fiber-filled compounds. The tensile properties of glass fiber-filled polyamide 6 modified with the malleated elastomers are quite interesting. When you take a bird's eye view to these slides, the bottom line is they show that by combining a hard material, polyamide 6, with the 30% glass fiber, and a soft but functionalized material, for instance, a malleated elastomer, it is possible to obtain a material which is harder than the original. Quite surprising. Both modulus and strength tend to increase with the malleated elastomer modification, and the gains can be as high as 20% for the new solution NMA-SEBS that we are proposing. Polyamide is hygroscopic, and for putting the absolute values of the properties into context, it is important to notice that the samples were fully equilibrated at room temperature, which means that prior to testing, they had very long time to absorb most moisture from the atmosphere, and at the point of testing, they contain something in the neighborhood of 3% of water. But how to explain these unexpected results? Here is a plausible explanation. Tensile properties of a composite are critically dependent on the bonding between the polymer and the filler, glass fiber in this case. For this reason, glass fiber producers introduce a coupling agent in their products, a low molecular weight compound that binds chemically to the glass surface on one side and it reacts with the polymer on the other side. Specifically, in the case of polyamide, the reaction is between the coupling agent and the acidic end groups of the polymer. The polymer molecules that are eventually grafted on the glass surface form entanglements with the surrounding melt. And this activates a very local and efficient stress transfer mechanism that boosts the tensile properties of the material. In summary, looking at the picture on the left, mechanical properties depend on the polymer glass fiber interfacial strength via the entanglements formed by the grafted molecules. More entanglements means higher interfacial strength, and this translates into better mechanics. Now, going to the picture on the right-hand side of the screen, when we introduce malleated SEBS in the system, we are introducing elastomer particles with the polyamide 6 molecules sticking out of their surface and terminated with the acid end groups. These acid end groups of the polyamide molecules tend to react to the coupling agent. In this way, the SEBS particles end up directly linked, pinned, connected to the glass fiber surface. Such a mechanism leads to a very high interfacial strength because of the size of the SEBS particles, they are very bulky, and the many entanglements that it forms with the surrounding. Eventually, this leads to an improvement of the macroscopic mechanical properties of the material. In summary, looking at the picture on the right, the basis for the observed improvement in tensile properties is the local interaction between the malleated SEBS and the coupling agent on the glass fiber. Going forward, it is important to realize that only a small fraction of the SEBS particles are needed in this mechanism. The rest remain dispersed in the matrix far away from the glass surface. And in all cases, SEBS preserves its soft characteristics. For this reason, the SEBS particles dispersed in the matrix, next to the improvement in tensile properties, we also see the classic expected increase in the impact resistance of the composite that is related to the deformation mechanism taking place in the matrix rather than at the interface. As you can see, the notched diode reaches a level of about 15 kilojoules per square meter for all modifiers. This plot is interesting because it directly shows the advantage that the novel malleated SEBS and also FG1901 bring. Impact in combination with stiffness. Indeed, it appears that the Kraton solutions really excel when it's about high impact in combination with high stiffness. Translating these to applications, high impact means durability or structural integrity, protection from unexpected sudden loading. Higher modulus, on the other hand, means potential to reduce part thickness, saving material and weight in application. And this broadens the opportunities for application using injection molding. Therefore, the strength of our product really lies in providing a solution that achieves a beneficial balance between impact, modulus, towards enabling lighter, tougher, and more efficient parts. Before we discuss the last technical topic, processability, we have one final poll question for you. We would love to hear your thoughts on what performance processability aspects are you interested to enhance the most in your formulation. Please select the option that should be appearing on the screen right now. Thank you, Julia.
Thank you, Luigi. Okay, interesting. So it looks like we have overall balance and properties leading, followed by impact strengths, and then we have a split view on the other aspects of it. Thank you for providing your feedback.
Thank you very much. Julia. Very interesting to see. Now, some final comments on processability. Next to the improved properties that I've highlighted so far, it is always important to be able to process and shape the material. The last thing we want to do is improve performance properties, but then make the part more difficult to mold or increase the scrap rate or the amount of defective parts. When we look at the processability in terms of flow characteristics or rheology more broadly, it is well known that modification with the maleillated elastomers leads to a reduction of the flow, degradation of the rheology in general. And this can be sometimes also severe. In this study, we observed that while all maleic anhydride modifiers lower MFR compared with the polyamide 6 GF30 reference, the novel maleillated SEBS mitigates the deterioration of the rheological characteristics and demonstrates an optimized MFR for injection molding between these samples. This is very important, especially in applications that require injection molding at thin wall levels. This brings me to the final slides. I would like to summarize the results that we shared with you today in my afternoon and probably your evening or your morning, depending on where you are located. We believe that the Kraton helps you create value by enhancing performance of ETPs in 3 different ways. 1, the ability to lightweight parts due to both enhancing stiffness and strength. 2, improve the processability with optimal flow. 3, deliver high impact at both room temperature and sub-zero temperature. With this, I would like to thank you for your attention and your participation today. I will turn it over to Julia to take the questions for the Q&A.
Thank you, Luigi. So we have a couple of questions already here and that people submitted in the questions tab, and you can use that as well if you have a question. So the first question we've got is about your benchmark modifier. So what is the benchmark modifier that we used? Can you tell a little more about that?
The benchmark modifier that we compared our solution against is a product, also maleic anhydride grafted, that is, we know it's widely used as a modifier in this industry. It is not of a block copolymer structure type.
Okay.
I hope this answers the question.
Yes, thank you, Luigi. The next question we have is about the data that we presented. So we presented the data focused on the glass-filled PA6. So the question is whether this data can also translate into PA66 or even glass-filled PP composites.
Yeah, thank you very much. This is a very interesting question that I would like to
No.
I'm sorry, I think the line went down
Yes,
for a
now
moment.
you're back.
It?
You're back, and maybe we'll have to turn off the video again because it looks like the audio is flawless without the video.
Oh, yeah.
Again, apologies.
I'm so sorry. I'll keep the camera off. So to answer the question, what you see on the right-hand side of the screen here is the mechanistic explanation of the molecular phenomena that are at the basis of this performance improvement. What I would like to say is that as long as such a morphology is realized, we will see the same directionally, the same type of benefits in fact, almost, I would say, any polymer, be it a polyamide or also a polyolefin. So you need the right balance of reactive centers, and then you can activate this performance gain almost in any composite of whichever nature. This is directional. The extent of the improvement will obviously depend on a lot of the molecular characteristics. In case attendees are interested in discussing a specific case further, we look forward to be part of that discussion.
Thank you, Luigi. The next question is, what happens to the polarity of this material? Will it remain polar or non-polar?
That's also a very good question. In fact, polarity, well, I should ask a question back. If it is about the interface of the material, the blend polyamide SEBS that is created, then that interface will lower its polarity a little bit due to the presence of the polyolefin at this point. If it is about in the bulk, maybe looking at compatibilizing or mixing in, blending in other components in this recipe, I think it will go in the same direction. The polyolefin, SEBS, being less polar than the matrix, will reduce the overall polarity of the system.
Mm-hmm. Yep. There is an interesting, thank you, Luigi. There is an interesting question. We are familiar with all the options of impact modifiers and use them frequently, but they always cause a drop in modulus. How is it possible that adding more rubber will actually increase modulus? So very provocative.
Yeah. Yes, of course. I also asked myself the same thing. I can tell that we have been repeating these tests more than once, 2 or more times, and it all hinges on getting the morphology which is on the right hand side of the screen, on getting it in the right in the material. So it's about when it's reactivity and it's about specific reaction centers. It's also about the feeding order in the of the ingredients in the extruder. In this case, it's very highly recommended to first let the polyamide react with the SEBS, and only later, at the very end, close of the extruder, close to the die, feed the glass fiber. This is common practice. Nevertheless, a lot of details may still be playing a role, and they can tip the balance of the properties in one or the other direction.
Mm-hmm. Thank you, Luigi. The next question is about reduced loss in modulus. Is it related to reduced moisture uptake with addition of our novel malleated SEBS?
Well, in fact, the SEBS is an apolar hydrophobic material. So yes, you can expect that the blend with the polyamide will absorb less water proportionally to the amount of SEBS. We're talking about, in these experiments, a loading of 10%. Therefore, rather than an equilibrium water content in the polyamide of 3.5%, it will be slightly lower. That's my take on it.
Okay, thank you. How to ensure this morphology is achieved? Can you suggest recommendations on the process conditions?
Yes, that's indeed a very interesting question, building on what we have said before. there are a few elements that count. In fact, it's a reactive extrusion process, right? So you need to, first of all, you need to have the right balance of the reactive centers. You need the polyamide, which is well balanced in acidic and amine end groups. If one of the two is missing because of one or the other development needs, then it will this morphology will likely not be there in place. On the other hand, it is necessary to use glass fibers that are suited for obviously for this kind of application, and they have a coupling agent based on amino silane type of molecules. Those are very prone to this to realize this morphology, and obviously the processing condition, temperature, moisture content of the melt, and so on need to be right. But I guess that people with experience in polyamides know this very well.
Thank you, Luigi. The next question, I think, is somewhat related maybe to the question before. How do we know the efficiency of the SBC? MA grafted, maleic grafted uses acid value. How about this SBC?
When you look at our portfolio, it's somewhere over here. All these polymers that are commercial. I cannot comment on the green, the novel malleated SBS. I cannot share details on that. But when it comes to the four commercial products that are in our catalog, the content of maleic anhydride ranges around 1%, a little bit up, a little bit down, depending on what the grade is optimized for. But the range is 1 ±%. Is that the question? Did I get it right, Julia?
Well, I think whoever asked the question, please, if it didn't, send the clarification question. If not, then we'll assume that it's addressed. But looking at the portfolio, I think there's a question about FG1901. So people were saying, well, we've been happy with your FG1901. So what makes our new malleated SCBS much better?
Yeah, that's also a great question. In fact, FG1901 has been a success, and it still is. It's a product that we are very happy with. It serves a lot of application. What we have done now with this experimental material, it's fine-tune the molecular characteristics for based on our knowledge for the modification of glass-filled ETPs. And you can see that, for instance, in this slide, that the modulus is a notch up with respect to what FG1901 can provide. And also, the flow is a notch better. And I think these are key characteristics that our customers can benefit from in developing their products.
Thank you, Luigi. Okay, the next question is about recycled PA6. Would our new product work with recycled PA in glass filled formulation?
Thank you. Also very interesting. Well, again, to answer this question, again, I have to go back to the molecular mechanism that is behind the observations. If the recycled product has the right reactivity characteristics, so a balanced amine acid end groups, and the glass fibers are fresh, which means the coupling agent did not react, then the chances are that it will work directionally in the same way. If by recycled the polyamide, one intends already a glass-filled polyamides, well, in that case, the coupling agent has been already used for reaction with the polyamide molecules, therefore is no longer available to graft the SEBS, and most likely this will, the benefits that we propose will not show up.
Thank you, Luigi. Okay. My experience with malated SEBS is that the thermal stability during compounding is sometimes less than malated POE. Is this still the case for our novel malated SEBS?
Yeah, that's also a very interesting question. Clearly, from an experienced engineer or scientist or product developer. Thank you for that. So it depends on what is meant here for thermal stability. The new product, in fact, I can say that is supposed to be more stable than FG 1901 and the allied for the way we engineer it on the molecular scale. Yeah, and this is partially shown on the slide where you can see that the drop of flow in terms of MFR is less than in the other two cases.
Thank you, Luigi. The question on the baseline for the 30% glass-filled BA6. So it looks like the strength and modulus values that we showed here are lower than people typically see. So were our nylon and glass selections unique grades, or could you comment, Luigi, on why the performance was so low to begin with for the unmodified glass-filled BA6?
Yeah, thank you, Julia. And to the person that asks this question. Now, the tensile properties, in general, the mechanical properties of polyamide-based composite depend critically on the amount of water that the sample has taken, that is present in the sample at the moment of testing, because water will plasticize the polyamide, decreases TG, and hence decreases the mechanical properties in terms of modulus and strength. If you could test a polyamide 6 containing 30% glass fiber immediately after molding, most likely the values that will be observed are somewhere in the range of 10, 11 GPa for the modulus, and maybe by heart 160, 108 for the strength, depending on the molecular weight that is used. Upon exposure to a moist environment, these properties will drop. And when the material is saturated with the equilibrium amount of water, typically the models will range between 6 and 7 GPa, and the strength between 110, 120 MPa. This is we measured like this because these are in fact the conditions that most likely the material will see in application. If we have, for instance, an EV battery enclosure made with such a material, this enclosure is exposed to the environment, and after some time, the properties of the material will lend to what you see here on the screen, fully equilibrated with the moisture content.
Mm-hmm. Thank you, Luigi. The next question is whether we tested the possible reduction in the glass loading beyond the thinner parts?
That is super interesting. Nevertheless, my answer is not as interesting. In fact, we did not test it. Unfortunately, you know, as I said when I passed by this slide, internally, we don't have the capabilities of working with these materials that are somewhat abrasive. Hence, our experimental, let's say, exploration is somewhat limited. That's a very good observation. One thing is to reduce the wall thickness of the part and save weight in that way. But another approach is also to reduce the grass loading, yeah, and increase the strength, the modulus, for instance, as I showed you. And in that way, you can have a part which has the same dimension, but a lower density. And eventually, this leads to weight saving. Yeah. Thank you.
Thank you, Luigi. Okay, the next question I think I can address. It's about our renewable feedstocks. So the question is, what kind of feedstocks are they based on for SCC Plus certified options? So typically, even though we have access to different types of the renewable monomers, we select the biocircular monomers, whether it's butadiene or styrene, simply because it really allows to maximize the value added of these materials, because they do come at a premium, and the biggest value added is beyond the certified biocircular content. Our customers can achieve up to 85% in the carbon footprint reduction when we look versus our fossil-based styrenic block polymers. And the biocircular feedstock itself is based on the second generation waste of either crude tall oil that comes from the pulp industry or the used cooking oil. Hope that addresses the question. And then the question around the samples, how can I get samples? So question, for samples, please reach out to Luigi or myself, and I will be happy to arrange the sampling process. I'll put the contact information for both of us in the chat. Luigi, there is an interesting question on the system cost performance balance. So typically people do the cutback blends with the SCBS and malleated SCBS when they modify nylons. Does our new innovation present any room for this type of approach to further use that let's say different loading levels of the malleated SCBS that we have plus the SCBS that is not malleated?
Again, lots of interesting questions. Thank you. I would be I think yes, and I would really be happy to explore this axis of the development together with companies that are interested in such a product. So
great.
Something we can work on together, certainly.
Wonderful. Well, it looks like we've addressed all the questions. Thank you so much for joining us today and engaging. We appreciate your time, and we are happy to engage with you afterwards to see how we can support you on your innovation journey. And with that, we're going to conclude the webinar. So thank you. Have a great day. And thank you so much, Luigi.
Thank you so much for having me. Thank you.
Thank you.
Bye-bye.